Now that we have learned about stars and constellations, let's think bigger. Why does the whole sky seems to move? So in this section, we will use the celestial sphere to explain the apparent rotation of the sky, how we measure positions with angles, and why your view changes with latitude. We will also see how stars move differently depending on where you look and touch on precision, the slow wobble of Earth's axis. So to understand how we observe the sky, we must first explore how Earth's motion shapes what we see above us. Ancient people saw the sky as a giant dome overhead, a big blue lid in the daytime and a sparkling ceiling at night. Pretty poetic, right? So even though stars are at different distances, it's helpful to imagine them stuck on a giant sphere around Earth. So this makes it easier to describe where things are in the sky. So the celestial sphere is what we call a scientific model. It's not a real sphere around Earth, but it helps us understand and describe the sky. So in science, a model doesn't have to be exactly true. It just needs to be useful. Let's take a quick guided tour of the sky. The next three principles will help you make sense of everything from star maps to why the Big Dipper disappeared in the southern hemisphere. Now, have you ever noticed how the sun and stars rise in the east and set in the west? That's not because they are moving, it's actually Earth spinning eastward. And it just looks like the sky is moving westward over us. And this spinning gives us day and night and makes it look like the sky is rotating over us like a giant dome. Now imagine you are standing on Earth. What you see above you is only half of the celestial sphere, the half above your horizon. So directly overhead is your zenith, and directly beneath you on the other side of the planet is your nadir. So this drawing at the right shows the view of an observer in North America. An observer in South America would have a completely different horizon, zenith and nadir. So here's something cool. The sky seems to pivot around the two invisible points, the North Celestial Pole and South Celestial Pole, which are directly above Earth's real poles. So right in between them lies the celestial equator. And where it meets your horizon are your east and west point. East and west points. So the directions we use north, south, east and west are actually defined by Earth's rotation and this celestial setup. So unlike roads and desks, we can't measure stars in meters or miles up there. So instead, astronomers use angles because we are measuring how far apart objects look, not how far they actually are. So we measure angular distance in degrees, arc minutes and arc seconds. So there are 60 arc minutes in 1 degree. That means 1 arc minute is 1 over 60 of a degree. And 60 arc seconds in 1 arc minute. That means 1 arc second is 1 over 60 of an arc minute. So yes, it's like time, but these are for angles, not clocks. For example, the moon and the sun both appear about half a degree wide in the sky. And the Big Dipper's ball, that's around 10 degrees wide. Pretty big on the sky. Here's how that works. Imagine lines from your eyes to two stars, and the angle between those lines is the angular distance. For example, the astronomer in the diagram would describe the distance between the moon and the star as an angle of 2 degrees. So to make things simpler, astronomers imagine everything: stars, planets, the moon, as they are pinned into a giant dome. the celestial sphere. That way, we can measure distances as if they are on a flat surface. Now, have you ever wondered why someone in Australia sees stars we can't see here? It all comes down to where you are on Earth, your latitude. So, your sky is unique. For example, people in Australia can see Alpha Centauri, a famous bright star in the southern sky, but they never see the Big Dipper. Can you imagine looking up and missing a star pattern you know so well? Think about that. Some of the most famous constellations we learn about just are not visible in the other parts of the world. So if you travel to the southern hemisphere, the Big Dipper would be a mystery. So this is super useful. The angle from the horizon to the celestial pole tells you your latitude. Sailors used this for centuries. Imagine starting at the North Pole with Polaris straight overhead. And as you walk through south, Polaris seems to slowly lower toward the horizon. It's like the sky itself is shifting. And at the equator, things get even more interesting. Polaris disappears below the horizon and the celestial equator passes right over your head. So your view of the sky changes dramatically. Have you noticed some stars never seems to set? These are called circumpolar constellations. They are like night sky VIPs, always visible because they circle the pole. So this figure shows a few circumpolar constellations. And if you live in the northern hemisphere, you can spot circumpolar stars like the Big Dipper, which orbit Polaris all night long without dipping below the horizon. So from places like the US, some constellations never disappear. They are your constant companions in the night sky. And up north, say in Norway, you get even more of these always visible stars because the pole is higher in the sky. But if you live on the equator, there are no circumpolar stars at all. Every star rises and sets every day, so the sky looks very different. And just like we don't see southern stars like Alpha Centauri from much of the US, those southern circumpolar constellations never make it above our horizon. So let's take a quick look at how stars move in the sky, depending on where you are and which direction you are facing, and clear up a couple of common sky myths while we are at it. So when we look north, we see Polaris, our North Star, barely moving. It stays put because it's aligned with the Earth's rotation axis. But stars like Ursa Major and Ursa Minor, they are circled around it. Isn't that amazing? Now let's look at east. Stars like Orion rise on curved tracks. Why? Because they are part of big circles around the celestial pole. The path seems tilted because of how we are standing on Earth. And from here in North America, you will see stars like Canis Major move in long arcs. But there are even more stars in the deep southern sky that we never see at all. They stay hidden below the horizon. So terms like celestial pole and circumpolar are important. But don't just memorize them, use diagrams to understand the motion. Now here are some misconceptions to clear up. The stars don't disappear in the daytime. They are still there. We just can't see them because of the sun's brightness. Now here's another misconception. Polaris is not the brightest star. It is actually the 50th brightest star. It's famous not for brightness but because it shows us true north, just the more useful. Now let's explore something subtle but powerful. Precision. It's a slow wobble in Earth's spin. and it affects what we see in the sky over thousands of years. Have you ever played with a spinning top? It spins fast, but its axis slowly traces a circle. So Earth does something similar. That slow wobble is called precession. So Earth is not just spinning straight up, it's tilted about 23.4 degrees of vertical. And that tilt is what gives us seasons, and it also affects how our sky looks over thousands of years. So because Earth bulges slightly at the equator, gravity from the sun and moon tugs on it, trying to twist the axis upright. That's what makes precession happen. So this is not something we notice overnight. One full precession cycle takes 26,000 years. But over centuries, it really changes what we see in the sky. So because of precession, the direction of Earth's axis point slowly shifts. So even the North Star changes over time. So because the celestial pole is just an extension of Earth's axis, when the axis wobbles, the pole moves too across these stars. And Polaris was not always the North Star. About 4,800 years ago, it was Tubanin Draco. In 12,000 years, it will be Vega, super bright and impressive. So let's look at this yellow dotted circle. It's the path the North Pole traces in the sky during 26,000 years. And that's why every few thousand years a different star becomes the North Star. Night to night, nothing noticeable. But astronomers using precise measurements like Hipparchus did over 2000 years ago can detect it over time. Now we have seen how the sky appears to rotate, how angles helps us to measure it, and how your location on Earth shapes your view of the stars. But the story of the sky is not complete without looking at its brightest and most dynamic players. Next, we will explore the sun and the planets, their annual motion, the change in seasons, and how planets trace out their own unique paths in the sky.